Hello, everyone. Let's talk about some more physics. What I'm showing here is going to be something that can be used in calculus-based physics, though many of the problems aren't really calculus-based problems, but they have a certain degree of difficulty that you could expect to see in a particular course that would be calculus-based, even if they're not calculus-based problems all the time. There's some that are calculus-based problems. In addition to that, many of these problems, very many of these problems are not calculus-based and can be used in a non-calculus-based class for review for that type of material. So it's very useful that way. So both the non-calculus-based class, content and review exams can be used in addition to this calculus-based review for a final exam as well. Both can be used. You just have to ignore the calculus that's being used in some of the problems, and all the other problems are very valid for non-calculus review. And in fact, I'll provide that for my non-calculus-based classes in mechanics and heat. And that's basically what we're doing here, mechanics and heat. For the people in the calculus-based class, the non-calculus-based review for the final exam is also good review as well. So I'll provide that for you as well, in addition to everything that's going to be here. Well, we're going to try to do this over, I think, 3 films from old exams that I had. And I also have 3 films for the strictly non-calculus-based content as well. So those 3 films and these 3 films together are really good review for the calculus-based review for the final exam. And they're also, those 3 and 3, those total of 6 films are also good review for the non-calculus-based review, for the final exam for the non-calculus-based material. All of the solutions for the practice exams that we're doing today are going to scroll at the end of each chapter. Forgive me, they're going to scroll at the end of each film. So all the content from the 3 practice exams, for which I'll make 3 films this time, and I've already made 3 films another time for non-calculus-based material. For this calculus-based material, I'll make 3 films from 3 old exams. We'll call them 3 practice exams. Altogether, those constitute a review for the final exam for the calculus-based version of mechanics and heat. With that in mind, and I'll have that on Canvas for people that are in my class, and they'll also be on YouTube, of course. In addition to all that, so every one of those practice exams will scroll at the end of each one of these films, just like every one of the content that was present for the non-calculus-based films. All of those practice films scrolled at the end of each film. So you're seeing everything at the end of each film, and then you're seeing each film covering in totality everything. Okay, forgive the convoluted nature of all this, but I guess it had to be said. Let's look at practice exam number 1, which was an old exam, and let's look at the solutions. Like I said, all of this will be available in PDF on Canvas, and all of this scrolls at the end of each film. So you'll see it there as well. So if it's not clear how I read off a problem, you can always look at what's scrolling at the end of each one of the films. Okay, so with that in mind, and I've got to check here, guys, the lighting, the reflection I'm dealing with sometimes with the lighting is not the easiest. So, okay, very good. So everybody should be able to hear me. Let's look at it. Exam number 1, Physics 209. Let's take a look at some of the stuff that's being asked there, you guys. So what we have here is this. Let me also have some different colored chalk here. that can also help us out a bit. But let's take it from there. Let me just quickly get me some different colored chalk, guys. That should be okay. Okay, guys, thank you for letting me take off a little bit. I just want to get some different colored chalk here a little bit, just to emphasize some things when we're doing some of this. Exam number 1, Physics 209. Let's look at number 1, see what they're trying to say here. Number 1, like I said, if this goes too fast, you can always go back and look at it. Obviously, there's the reverse feature. I always forget that. But also this stuff scrolls at the end. All of this, all 3 practice exams, scroll at the end of each and every film that I make regarding the practice exam for Physics 209, calculus-based treatment, regarding mechanics and heat. Number 1, a boat moves at 10.8 meters per second relative to the water. If the boat is in the river where the current is 2 meters per second, how long does it take the boat to make a complete round trip of 1,100 meters upstream followed by 1,100 meters downstream? So, okay, it's pretty somewhat basic. All these problems are somewhat basic, guys. It doesn't mean that they're easy. Any problem can be made, can be made pretty difficult for us. But the situation is, if you're going upstream, you're covering this much ground at the still water speed of this minus the fact that you're fighting the current. And that's going to take T1 to get you there. If you're going downstream, you are going the still water speed plus the fact that the current's helping you, and you're doing it in T2. T2 is probably a lot less or somewhat less time-wise. The total time is T1 plus T2. So we have what we have. All right. If you take this one, this problem right here, and solve for T1 by dividing by this quantity on each side, this one right here, divide by this quantity on each side. So you can solve for T1 by dividing by this parentheses quantity, solve for T2 in this equation by dividing by that parentheses quantity, and you're basically looking at a situation where the total time t is T1, which is all this divided by that quantity. Well, that quantity is 8.8. So it's 1,100 divided by 8.8. The other one is this and this. It's 12.8. Divide on each side. And that'll get you there. At the end of the day, that is 211 seconds. We can convert that to, heck, we can convert that to any time frame that we want. We can convert it to minutes. I mean, if we want to get ridiculous, we can convert it to hours, we can convert it to years, we can convert it to decades, you name it. But there we go. So you got that right there. Should be enough, given the options that are made available to you. Let's look at 2. 2 is saying, an astronaut applies a force of 450 newtons to an asteroid, and it accelerates at 7.0 meters per second. What is the asteroid's mass? Well, the next, I don't want to get into all the what ifs here. Let's say that the astronaut basically can do that, and that's the force that the asteroid is experiencing, and this is the acceleration it experiences. What is the asteroid's mass? Should be pretty straightforward. Force equals mass times acceleration. If you divide by mass on each side, acceleration is force divided by mass. That's true. But, you know, I think that is true. That's true. But maybe it's an easier way to look at it would be take this guy and divide by a on each side. And that's the one you want to look at. Because they gave you everything but the mass. So you got that right there. And that's where you're going to go. You will apply. You will look. You will say, M is 450 divided by 7, force divided by acceleration. Mass is 64.3 kilograms. And there we go. And that's for 2. For 3, an automobile of mass 2,500 kilograms moving at 50 meters per second is braked suddenly with a constant braking force of 8,500 newtons. How far does the car travel before stopping? So there's a mass, there is a speed initially, there's a braking that happens by a constant force. That force allows the car to stop. The greater the force, the faster the car is going to stop. The less the force, the longer it's going to take for the car to stop as far as distance is concerned. All right, so we're looking at that. You could say, well, they're telling us a bunch of things. We want to bring this thing to a dead stop. To bring it to a dead stop, we use force equals mass times acceleration initially. Force equals mass times acceleration. We're going to play the same game, kind of what we did earlier here. We didn't end up having to use it here when you're dealing with this, but here you could have used it. Here you use this. So let's see what we have here. All right. I'm always checking the audio, guys. All right, so we're okay. All right. So we have height. Let's figure out what kind of acceleration we need here. Well, it's braking, so it's a negative acceleration. In terms of magnitude, you got this. This is the braking force. This is the mass of the vehicle. Braking force, mass of vehicle. The acceleration in terms of magnitude is 3.4 meters per second. We will say negative because it is a braking force, so apply the vector that way, and then find out how long of a distance we're talking about. You guys remember from work that we've done that D, well, there's a lot of ways to write D. We got this. We got that. The final speed is 0. The initial speed, they told us, was 50. The acceleration is negative 2.4. Forgive me. The acceleration is negative 3.4. 2 times negative 3.4 is negative 6.8. The rest is just math. According to this, it's a very large vehicle, remember now. It's going to be hard to stop a very large vehicle. And, it's a relatively large vehicle. The force maybe is not something profound enough to stop it sooner. What we get here, it's a lot. It's a long time, or a long distance at the very least. How long it would take, that's an interesting matter in its own right, how you'd solve something like that. Distance is that. Whole lot you could say there, I guess you could say. When you're looking at something like this, look at nobody asked you to go any further than this, but if you wanted to find the time, you'd be looking at an equation. Nobody's asking you this. This is the answer. You got it. You're done. But you could also do VF minus VI divided by A. Nobody asked us. But, the final is this. The initial is 50. The acceleration is negative 3.4. And this is going to be negative 50 divided by negative 3.4. Do not have a calculator on me right now, guys, and we're not even being asked to do this. But you get the idea here. Negative divided by negative is a positive answer. Trying to think about where it's going to go. In the ballpark of about 15 seconds. Not quite. It's a little on the high side, but somewhere between 14 and 15 seconds is just my view on where it's going to be. It takes a long time. It takes an awful long time-wise and distance-wise. It is really, it's really going a long time. All right. Didn't ask us this, but this is, if they wanna make this problem continue to be kind of interesting, they could go here and we could grind out the mathematics. Nobody asked us, but we could, or they could. So for number 4, you guys, a boat with mass 1,200 kilograms is traveling at 12 meters per second. What is the magnitude of the force required to stop the boat if it undergoes a displacement of 85 meters? The longer the displacement, the less force can accomplish that task. If you really want to stop it quickly, the force has to be over not much of a distance. If you really want to stop it, then you're going to need a lot of force. So that's interesting how that plays out. As we look at this, we're looking at, we could come back to things we've already seen at one point or another. In fact, very recently in this very film, we've seen this. We've got this. And if you want to play the game, you can solve for A, wheel and deal when you do that. And, this equation right here, multiply by A on each side and divide by D. And we've been here. We've done this. And that's really, that's a lot of the problem. It's not the whole problem, but it's a lot of the problem. What we can do here is say, okay, well, let's plug in everything and go. A is going to be, you got to bring the final to 0. The initial is 12. 2 is 2. D is 85. And there you go. Grind all that out, you guys. You got A is equal to negative 0.847 meters per second per second. So okay, they didn't really ask that as a final answer, but it is an answer that you indeed have to get. Regarding the force, the magnitude of the force, force is equal to mass times acceleration for our purposes right here. It is a 1,200 kilogram boat. We need the absolute value of this just to get magnitude. Mass times acceleration will give you the magnitude of what we want. The magnitude of the vector, you want to call it F like we were doing it earlier, is 1016.5 newtons. Okay. Sounds good. All right. Let's keep going. 5. What is the momentum of the block? Let me see here. What just happened here? Okay, here we go. I'm sorry, guys. All right. That was 4. 5 I don't start looking at the wrong stuff, I'll just turn this upside down, guys. For number 5, a train slowly climbs. For number 5, a train slowly climbs a 400-meter mountain track, which is at an angle of 8 degrees with respect to the horizontal. How much altitude does it gain? So a train slowly climbs a 400-meter mountain track, which is at an angle of 8 degrees with respect to the horizontal. How much altitude does it gain? It's a lot easier than potentially we could make it for ourselves. We just got to be a little careful, that's all. So for number 5, you're just drawing triangles. So let me see what we can do regarding this. Sometimes I'll put it on pause and do it, guys. Hopefully I can get through this relatively quickly when I'm doing it. Okay, so guys, it's perhaps a lot easier than it might look when we're doing this. What you're seeing is, okay, what kind of an altitude climb are we talking about? Let's call the altitude h. Let's call this theta. Let's call this total distance right here. Let's call it d. And from there, we know that h over d, opposite over hypotenuse, is the sine of theta. If you multiply by d on each side, h is d sine theta. Basically, you're plugging in the numbers here. We don't know h. This is 400. Theta is 8 degrees. So let's see. Grind out the numbers, guys. What we're looking at is a climb of 55.7. And that is 5. Let's have a look here. Let's look at 6. A cheetah can maintain its maximum speed of 96.0 kilometers per hour for 26 seconds. What minimum distance must a gazelle running at 85 kilometers per hour be ahead of the cheetah to escape? It's a great question. There's a lot you can do. Let's compare the speeds, you guys, and find out what we're doing here. I'm always checking here, guys. It's a little. There's some wonderful people helping me do all this stuff, and they're working with conditions that are sometimes, sometimes pretty challenging. But it's a wonderful environment at the same time as well. Fortunate to be able to do this. So, always checking to see if the audio is okay and that you can see me okay. I'll do my best on that. Well, let's take a look, guys. The cheetah is going 96 kilometers per hour for 1 hour. let's go meters per second. That seems to be the lingua franca on this whole thing. 96 kilometers is 96,000 meters. 1 hour is 60 minutes. Every minute has 60 seconds. 60 times 60 is 3,600. Take these two, do the division. The magnitude of the velocity of the cheetah chasing the gazelle is 26.67 meters per second. Okay, that's moving. That's definitely moving. That is about, if you look at an Olympic sprinter doing the 100 meters, an Olympic sprinter doing the 100-meter dash in 10 seconds, let's say, it's pretty elite. There's better times than that even, but let's go right about at that level. 100 meters in 10 seconds, that's 10 meters per second. This is more than 2.5 times that regarding speed. Pretty fascinating. Now, let's compare that to what's going on with the cheetah. That was the cheetah, with the gazelle rather. You've got 85 kilometers per hour. That's 85,000 meters divided by 3,600 seconds. We're converting everything to meters per second because they phrase the problem in a certain way. Do this mathematics here, and you get via the gazelle. Via the cheetah is this, via the gazelle is that. We got 23.61. So we got via the gazelle, we got via the cheetah. Obviously, if they start fairly, the gazelle is going to lose. So let's see how they're going to do this. You got to make it so there's at least a tie, and then there's a chance to get away. You got to go this fast or faster. So let's see how they're playing this. We're figuring at the same amount of time. They both start running, and they run for the same amount of time. The cheetah is going to cover. The cheetah is going to cover v sub c times t distance, and the gazelle is going to cover v sub c times t is for the cheetah. V sub g times t is for the gazelle, but the gazelle's got to have a head start. If not, the gazelle loses the race. And it's a tough race to lose, obviously. So you look at it, you say, okay, that's how I'm going to play it. Let me see what d is. What's the minimum distance he can be in front? Let me subtract v sub gt on each side. So you're looking at something like this. You got that right there. So what's going to happen is d is going to be, factor out the t. We got this right here. Okay, let me try to, they're saying I think 26 seconds was put in there, that the race is going to take place. Yeah. Let's assume that the gazelle is, we got to use Occam's razor here a little bit, guys. 26 seconds is the duration you got. Let's see what we can do. The rest is pretty straightforward, you guys. We've got D right here. We've got the cheetah, 26.67. The gazelle, 23.61. And we got the time of 26 seconds. And there you go. Well, yeah, it's quite a lead that better be had. 79.4 meters at the least. $79.4 meters at the least for that to happen. Okay, pretty fascinating stuff. Let's take a look at number 7. So we got, as we said, 79. I hope I said it right. I sometimes mix up the numbers here. 79.4 meters. Yeah, right there. 79.4 meters. 7. A cement truck can pour 160 cubic yards of cement per hour. Express this in feet cubed per minute. Not too bad. Not too bad, but we got to be careful. We'll be given enough information to make this make sense. Some things we have to memorize, other things we don't. There has to be a decent conversion factor here to make this happen. So let me see. That was 6. Now let's go to 7, you guys. Let's see. Oh, no, actually, no. The conversion factors aren't too bad. Aren't too bad on this one. 1 yard, it's kind of a fascinating argument in its own right. 1 yard is 3 feet. 1 square yard is a yard times a yard, which is 3 feet times 3 feet, which is this. 1 cubic yard is 1 yard times 1 yard times 1 yard, which is 3 feet times 3 feet times 3 feet, which is 27 feet cubed. Pretty important stuff. Now that's reasonable for people to be able to do it. We know what a yard is. It's 3 feet, and from there we can figure out what we're doing. 160 yards cubed per hour. Well, we already said that an hour is 3,600 seconds. 160 cubic yards. Every cubic yard is 27 cubic feet. 27 cubic feet. So we got 160 times 27. Get an answer. Divide it by 360. Some pretty neat stuff you can do here. You can do a lot of this in your head. Well, kind of pushing it, doing your head here. You could pull a 9 out of here. You could make 27 3 times 9. 9 cancels into here, and it becomes 400. So you could say 3 times 9 is 27. 9 goes into here 400 times. Then 3 times 160. 4 times 40 times 3. 4 times 40 times 3. The 40 and the 400, they cancel. You got a 10 down here. So it's 4. So basically, that's kind of an interesting thing in its own right, I guess you could say, the way we did that. So we could say, you could do this in seconds. I'm about to do this in seconds, and I think maybe that's not the greatest idea. Well, I entered the dance. I got to do the dance, I guess you could say. 3 times 9 is 27. 9 goes into here 400 times. 3 times 160. So 3 times 160, I guess you could say. So 4 times 40 times 3, 4 times 40 is the 160. 4 times 40 times 3 times 9. The 9 cancels into here, you got 400. The 40 and the 400 cancel, you got 10 down here. You've got 4 times 3, that's 12 over 10. That's 12, that is, let me just make sure we got this straight, you guys. Yeah, absolutely. That would be 12 over 10, 12 tenths feet cubed per second. If you were to do this, for some reason, I'm almost not even agreeing with the answer I'm getting here, but let's quickly view it. Yeah, I think it's looking pretty good here. You got 400 here. You got here, that's 10. 4 times 3, that's 12 over 10. If you were to multiply, no, that works just fine. 12 tenths, so this, if you play this game here, guys, you get 12 tenths feet cubed per second, per 1 second. That's great, but they're not asking you that. They're asking you per minute. Well, make this 60 seconds per 1 minute. So you multiply this by 60. If you multiply this by 60, you get 720 over 10. 720 over 10 is 72 feet cubed per minute. Forgive the roundabout way of doing this, guys. You could have killed all the birds with one stone had you right off the bat looked at this thing and made it go, you play the game here, you got what you got here per hour. Well, yeah, you could do this and then get this right here. There's nothing wrong with this. This is 6 over 5. This is 1.2. If you take 1.2 and multiply it by 60, you get this. Not a problem. You could have taken it and gone, like I said, the 160 times the 27 feet cubed per yard. 27 feet cubed per cubic yard, there's 160 cubic yards. An hour has 60 minutes to it. And these are feet cubed right here. That works. I mean, you could play the same game here. You could make this 3 times 9. You could make this, you could do a lot of things here. You can make this 3 times 9. You can make this 4 times 40. 4 goes into 60 15 times. The 40 remains. 3, so 4 times 40, 3 times 9, 4 times 40, the 4 goes into 60 15 times. You got the 40 left over. The 3 of the 3 times 9 goes into 15. You got 5 left over. You've got 9 times 40, right? Yeah, right. I mean, so the way that would, forgive what's going, yeah. So 4 times 40, 3 times 9, you could say the 4 goes in here 15 times, the 3 goes in here 5 times, so 5 on the bottom. And from here you go 40 times 9, which is 360. 360 divided by 5, bam. Okay, again, this could have been done about 5 minutes ago, but this is kind of the argument to go to and save yourself a lot of time. If you go to seconds, you're getting this for an answer, then at that point, you can multiply by 60 seconds for every 1 minute, multiply the thing by 60, and you are getting that anyway. So it's going to work out. Anyway, some neat, potentially interesting mental gymnastics we can do regarding that. Obviously, on an exam, you guys, you don't want to sit here and prove a lot of mathematical identities. Just get it done. But, all right, I had started that. I might as well finish it. That was 7. 8. Planet Z, for number 8, on planet Z, the standard unit of length is the foot, and the astronaut is 5.2 feet tall on Earth. She lands on planet Z and is measured to be 88 foot tall. Her partner Rachel is 72 foot tall. How tall is Rachel on Earth? So they're giving us an identity here, and they wanted us to do a couple things with it, and let's see how the whole thing plays out. So that is for number 8, you guys. So let's see what we got here. Right. Okay. Okay. Old school proportions here, guys, and so much of what goes on in mathematics and physics pertains to proportions. So let's take a look at it a little bit, guys. Well, if we're talking about foussi, and the plural of it is foussi, if one person is if one person is 92 and the other person is 88, tall divided by short is going to be tall divided by short. The person who's 5.2 is corresponding to 88. The person who is X corresponds to the 92. It's that simple. The rest is solving a proportion. You've got 88 times X times 92 times 5.2. Divide by 88 on each side. Let me try. I'm not sure how this gets viewed sometimes, guys, so I'll try to get out of the way a little bit. So divide by 88 on each side, guys, and it's just going to spit it out. And I've got it a little more explicitly in the PDF solution. So they're going to be taller. Yeah, if one person is 92 and the other one's 88, 92 is taller than 88. So X is going to be more than 5.2. And that makes sense. And that's that. Let's go to 9. 9, this is an interesting problem. Let me try to draw it better. Well, let me try to draw it okay. And again, the PDF's got more substantial detail than I think I could probably put in there in an efficient manner. Let's take a look. Okay, guys. For number 9, there are 3 blocks in a figure, folks. And it's a frictionless surface. If there's a force, F equals 48.0 newtons, and an M1 equals 2 kilograms, and M2 equals 1.5 kilograms, and M3 equals 3.5 kilograms, what is the tension in the cord? Okay, let's try to make this make a little bit of sense. Again, the drawing that you'll have in regard to the PDFs is going to be not bad. It should be pretty good for you guys. Okay, so this is the floor. It's frictionless floor. Okay, this is M1. This is M2. This is, over here, M3. So it's got to be a little bit larger, probably the largest of all of them, I guess. And there is a rope between them. And there is a force. There's a force pulling right here, and that's F. Don't know how visible this stuff is. In the past, when I've made these films, it's pretty visible, but let's do that. That's the force F. They drew it green here, so let me try to draw it green without getting too messy here. The other one is kind of like blue. I don't know. The other one's brown. So I am definitely running out of colors here, guys. I'll make it like this. Again, you'll see this when you're dealing with all this stuff there, guys. They are telling us the 3 blocks are the three blocks in the figure are on a frictionless surface. F is 48.0 newtons. I'll just write it like 48. M1 is 2 kilograms. M1 is 2 kilograms. M2 is 1.5 kilograms. M3 is 3.5 kilograms. Okay, I think we more or less got this under control that way. What is the tension in the cord? It's a great problem. It's a great problem. Basically everybody's getting pulled. Everybody's kind of sort of attached in a somewhat complicated manner, but nevertheless somewhat attached. There's M1, M2, M3, and they're all going to move. If they're all going to move, that force is going to move all of them. True. But that tension right here, in here, is not moving M3. It's moving those two. So if you can figure out the acceleration that's being provided, the acceleration times the sum of the masses M1, M2 will give you what the tension in the cord is. That's kind of the argument. So let's take a look at it. It's a fascinating problem, and it's simple yet a little on the very interesting side. All of these together are moving that way. All of these together are moving that way with the same acceleration. Sum all these masses together. Sum all these masses together, and M1, M2, M3, that's the total mass. Divide that into the force, that's the acceleration of all of these, because they all have the same acceleration. Therefore, take these two masses, their sum, and multiply by the acceleration. You know what the tension is. For some reason, okay, so yeah, that's basically what I was doing here, guys. Let me just kind of look at it and see what we have. So we have 9 here. We just said 9. Let's see what we have here, guys. So what you're saying is, essentially, the acceleration of all 3 of these is the force divided by the total mass. The total mass is the sum of these 3 masses. Sounds good to me. That is, they're telling us the force is 48. The total mass is the sum of M1, M2, M3. That is 2, 1.5, the sum of 2, 1.5, and 3.5. And what it's getting us is 7 kilograms. There it is. The acceleration is 6 6/7. Now, I may want to go with decimals. I may not. Depends what's easier. Sometimes it's easier to deal with fractions. Other times it isn't. Well, that's the acceleration of all of them. Interesting. What about the tension? The tension only pertains to what's getting pulled. This is one block in a sense, and it's pulling these. I mean, this is one whole situation pulling these. The amount of force on these is interesting in its own right, I guess you could say. But there's a lot to be said. Maybe I shouldn't say too much, at least for now. Let's just get through these exams while we're doing it. You're talking about a situation where the tension and this will be the tension, so I don't, tension T, pulling that way. I don't know that that's the greatest drawing in the world, but let's keep going. We are talking about the tension being, it's a fascinating problem. The two of those together is 2 kilograms plus 1.5 kilograms. 2 kilograms times 1.5 kilograms. Right, that's 3.5 kilograms times the acceleration that's taking place, which is 6 6/7. Again, you can go to decimals you can go to decimals right here. I tell you what, maybe there's an easy thing to look at here. Is 3.5 the same as 7/2? is 6 times 7, 42, and 6, 48. So it's kind of neat about this whole thing. The 7's cancel. The 2 goes into here 24 times. So it's kind of interesting. Again, even with the decimals, you're going to get awfully close to it. The tension's going to be 24 newtons. Okay, great problem, guys. Great problem. Number 10. Suppose a particle is moving along a straight line with a speed v for a time t, then stops for a time t, and then resumes moving along the original direction with speed v for time t. What has been the average speed of the particle for the total time period 3t? Okay. It's probably easier than it sounds, or maybe it doesn't sound too hard. For number 10, we know as a general rule, v is distance. I don't want to get into vectors and scalars or whatever. Let's talk about speed. Let's talk about one direction, no change in direction or anything like that. Let's deal with it. If there is a change in direction in the just one-dimensional realm, it'll be a positive or a negative associated, and we can still play this game. It gets a little more complicated when we're talking about more dimensions, 2 and 3 dimensions. For right now, one-dimensional space is what we're talking about. V is equal to d divided by t. D is equal to v times t. In general, not just for this particular look at this. Well, I'll tell you what I'm going to do. For our purpose, in general this is true, and even specifically, let's use the v and the t that they have told us about. I don't think they brought up a d in here when they did it. Let's see. No, they did not, but we brought up the d. We'll say the d is associated with how far you're going to go in time t associated with v. This will be the reality. Okay. Well, what's going on here? Well, the thing went d amount of distance, then it stopped. In a time t, it went d amount of distance. In another time t, it went nowhere. And then another time t, it went d. It did this over a time t, another time t, and then another time t. That's how it all played out. Well, if that's the case, that's all you need to worry about. The average speed that's going to be associated with this is going to be, add the tops, that's 2d, add the bottoms, that's 3t, and at the end of the day, you've got 2/3 times d over t. Well, didn't we already make the claim that d over t was v? So the average speed drops because you did stop. You stopped for 1/3 of the time period that this thing was going, for the total 3t. That right there is v, and that's where they're getting that. So they're talking about 2/3 v on that, the way that they place this argument. So 2v over 3 is the way they give it. 2v over 3 is the same as 2/3. 2/3 v and 2v over 3 are the same thing, obviously, guys. So we know that. All right, let's keep talking. Let's look at number 11. Number 11, a bullet is fired through a barrel. Number 11, a bullet is fired through a board 1 meter thick with its line of motion perpendicular to the face of the board. If it enters with a speed of 700 meters per second and emerges with a speed of 100 meters per second, what is the bullet's acceleration as it passes through the board? It's not too bad of a problem, guys. Not too bad of a problem, but we got, like anything else, we just got to know how to do it. All right, so Okay, so what's going on with this thing? Well, I mean, it's a remarkable occurrence in its own right. I mean, I wonder how strong this board is. It's a 1 meter thick board. Let's have a look. So basically what they're doing here, guys, if you want to find the acceleration, and they're given the answer in different ways, so we'll answer the way they're telling us to answer. But we know enough. We've seen a lot. We know this is true. Manipulation of some of the kinematic equations will get us there. The final is 100 meters per second. The initial is 700. The distance is 1 meter thick. We're keeping this in the MKS system of units. As this proceeds, you square the 100, you get 10,000. You square the 700, you get 49 followed by 4 zeros. So it's quite the situation, I guess you could say. So what we have here is this. That's a lot. I mean, and you got this. You got 2 times 1 is 2. The rest should go pretty straightforward, my friends. Negative 240,000 convert meters to kilometers. This is a remarkable acceleration taking place in terms of magnitude. That is it. That is it. Some remarkable numbers, guys, that are occurring here theoretically. Let's go to 12. Let's see what we got here. For number 12, the position of a particle moving along the x-axis is given by, now here's more, now all of this, all the way up to this point, did not require calculus. So people taking a non-calc based version of this kind of a class, mechanics and heat, this is good coverage. It's good coverage of it. So, and for us that are doing the calc version, again, here's an example of it. Number 12, the position of a particle moving along the x-axis is given by x equals 5t squared minus 2t to the third, where x is in meters and t in seconds. What is its maximum speed? Should be pretty straightforward stuff, guys. Again, this is more calc-based version at this point. So other people that aren't taking a calc-based version of the class, all of this is really good review. If you want to look at this as well, go do so. You won't be held accountable for a calc-based problem unless you're in a calc-based class. So x is given by so the min-max is going to occur when the first derivative is equal to 0. So go dx dt, and that's going to be that right there, that's the first, well, let me say a lot of things. What I just said is true. The min-max in regard to x is going to occur here. That's true. This dx dt is v. And dv dt is the first derivative of v, or the second derivative of the initial situation that was presented to you. We go here, we got 10, so take the second derivative here or the first derivative here, same thing. Go here, and we got 12t. And that's going to be equal to a. So we'll see how they proceed with this, guys. I want to make sure I kind of dot all the I's and cross all the T's on this thing. Just so we know, we got this. How much we need it, we'll see. We also got this, which is equal to A. So it's pretty interesting that way. We got the A here and the V here. And so let's see here. A number of ways you can go here. I guess you're trying to find the V max. So to find the V max, you got the V right here. If you wanted to find the X max, it's associated with setting the first derivative of the X function equal to 0. If you're trying to find the V max, it's associated with setting the first derivative of the V function to 0. So if you set the first derivative of the X function set equal to 0, you will get the maximum X when you get the first derivative of the X function. First derivative of the X function set equal to 0 will give you what the maximum X is. The first derivative of the first derivative, in other words, the second derivative of the X function, which is the first derivative of the V function. First derivative of the V function set equal to 0 will give you the time in which V is at a maximum. So make the long story short, I guess you could say. If A is, when there's no more acceleration, you're going to hit the maximum velocity. And that's the acceleration, that's dv dt, and when you set it equal to 0, there's no more acceleration and you reached your maximum velocity. If A is equal to 0, you've got 0 equals 10 minus 12t. Solve for t, add a positive 12t on each side, divide by 12, the whole song and dance. At 5/6 of a second is when you have reached your maximum velocity. So okay, great. Well, what is the equation for the V function? The V function is this, 10t minus 6t squared. 10t minus 6t squared. Let me just make sure. Yeah, 10t minus 6t squared. Let's go. V is 10, 5 over 6, minus 6 times 5 over 6, the quantity squared. All right, I mean, it's a little bit of, a lot of movement here, guys. That'll give you the max. V max is 4.17 meters per second. Definitely a calc-based problem right there. Okay. That should be okay when we do that. That's 12. 13. A particle moving along the x-axis has a position given by x equals the quantity 100t minus 10 t to the third meters, where t is measured in seconds. What is the magnitude of the velocity of the particle at the instant when its acceleration is 0? When its acceleration is 0, we kind of played that game over here. The acceleration being 0 was the max. That was going to happen in that regard. So let's take a look at it. Basically, let's play the same game. They phrased it in a way that perhaps could challenge us, but we can do it. X is 100t minus 10t to the third. Well, here we go again. To find the velocity, v is dx dt. Calculus-based problem again. Dx dt is 100 minus 30t squared. That's what v is. The acceleration is 0 is what they're talking about. Well, what is the acceleration? Acceleration is dv dt. Is the first derivative of this. The derivative of this guy is v, And then the derivative of this will give you acceleration. So take the derivative of this. dv dt, take the time derivative right here of this function, because it is associated with v. We're getting negative 60 t. So that's the acceleration. When the acceleration is 0, forgive me, that should be a negative right here. The acceleration is 0, t has to equal 0. So I'll put t equals 0 right here. 0 times negative 60 gives me a equals 0. A equals 0. If a is equal to 0, the only way you get a equals 0 is if t is equal to 0. Okay, sounds good to me. That's when Vmax occurs. What is Vmax? Vmax is going to be 100t. Forgive me, no. Vmax is going to be 100 minus 30 t squared. And again, it kind of goes with our common sense. If you're to graph this parabola, folks, where's the place where it's going to be at its highest? If you graph this parabola, it's going to be at 100. When is this number going to be at its biggest number? When's the number going to be at its biggest number? Well, I don't know. I want to subtract as little as possible. And since there's no such thing for us as negative time, and I'm not going to get a negative, minus a negative will make this bigger, but I can't make this negative. If I square any real number, it's a positive number. A positive number times this is positive. I'm subtracting. This thing's getting smaller and smaller. The only time this thing is going to be minimized at the most is if t is equal to 0. We already kind of see it looking at it. You can kind of get away with that. So you go here. And let's see what we got, guys. Put a 0 right here. Vmax is 100 meters per second. So, let's see what we got here. Right. Let me, just in case the sound thing came off a little bit, guys, I just want to make sure we have it all straight here, if we can do so. Let me just come back here a little bit. I don't think it's been a problem, but again, if you're shooting a bullet through a board, this is the exit. This is the magnitude of the exit velocity, 100. This is the magnitude of the entrance velocity. You're using this formula. You grind it out. You convert it to kilometers per second squared. You get this. That's number 11, just in case something got messed up, because the audio is not great here. My fault. I might have hit it or something and shut it off. But okay, we have this. I think you probably already have that. But we have this. It's on the board. Obviously, you can see it. Now you're hearing me say it, okay? Here's number 12. How are you going to find the maximum velocity? Well, this is this. If you take the first derivative of x, you get velocity. If you take the first derivative of x, you get velocity. If you take the second derivative of x, you get acceleration. Another way to put it is, take the first derivative of x and get velocity. Take the first derivative of velocity, get acceleration. You want to find acceleration at a maximum, so it has to be equal to 0. To have it be equal to 0, you solve this for acceleration to be at a minimum, for acceleration to be at a maximum, max or min, in this case maximum, and we find at this time acceleration will be at the maximum. Forgive me, it could be at a maximum, it could be at a minimum. In this case, it's a max or min. For our purposes, we're looking for a minimum. This is minimum acceleration. So we get a is equal to 0, minimum acceleration. Once you have minimum acceleration, you've reached the peak speed. Put that time into the velocity equation, folks. You got this right here, and then you have the answer. Same thing here. They give you this. This is for x. If you take the first derivative of x, dx dt, you got v. If you take the second derivative of x, you got dv dt, which is acceleration. Put another way, First derivative of x is v, that's dx dt. First derivative of v is dv dt, which is a. So first derivative of x, dx dt is v. First derivative of v is dv dt, which is a. Where is the acceleration going to be equal to 0? At t equals 0 is where that's going to happen. Okay? At t equals 0. So that's where the acceleration is equal to 0, and that is when you're going to get the maximum v. Put in time t equals 0 into the equation for the v, and that will be v max. Put a 0 right here, and it makes sense. You're always taking something away unless you don't take something away, and you won't take something away if t is equal to 0. That's where the v max is going to be, and you get that for an answer. I'm sorry, guys. You probably saw that over 10, 15 minutes, but I'm afraid that just to be safe, I'm afraid that I may have shut something off. I'll try to keep a closer eye on this thing, but I think you see where I'm coming from. Anyway, should be pretty good for us. That is all the way through 13. Let us proceed. For number 14. For number 14, a stone is thrown from the top of a building. A stone is thrown from the top of a building with an initial velocity of 15 meters per second downward. The top of the building is 150 meters above the ground. How much time elapses between the instant of release and the instant of impact with the ground? Straightforward problem. Great problem, pretty straightforward. Let's get an idea where it's going. All right, guys. Relatively straightforward. You gotta again watch it. Just make sure everything's the signs are all where they should be. So what we have here D equals VIT plus 1/2 AT squared. Okay, just be careful. That's it. That's the thing. You are going to, since everybody is falling straight down, you don't have to use negatives. If you are going to use negatives, then everybody has to be negative. The acceleration due to gravity has got to be negative 9.8. The height has to be, I guess you have to say, since it's going downward, the D has to be negative 150. The A has to be negative 9.8. The velocity's got to be a negative as well, if you're going to call things negative. Strictly speaking, you can do that. Strictly speaking, maybe that's what's going on anyway. However, since everything is negative and there's no up and down on this, you can call everything positive, and it makes it a lot easier to work with. But again, be aware of that subtlety, guys. The fall is 150. 15, so everybody's going in the same direction down. If everybody's going in the same direction down, you can treat everybody as positive. If something was being thrown upwards, however, you really have to pay attention to the signs, positive and negative, when you're doing that. Here's 150, here's 15. I don't know what T is. A is 9.8. 1/2 times 9.8 is 4.9. This is the equation that has to be solved for T. You can write that as 4.9 T squared plus 15T plus a negative 150 equals 0. T is like the x. X is equal to the opposite of B. This guy is B. This guy is A. This guy is C. A, B, C. Okay? T equals the opposite of B plus or minus the square root of the quantity, B squared minus 4AC. C is negative 150. You've got to do the math. Over 2A, which is 2 times 4.9. Okay, grind out the answer, and let's see where this is going to go. You should get 2 solutions here. One of them should be absurd. 4.21 seconds. And that's that. That was 14. Go to 15. Uh, 15. A rock is thrown downward from an unknown height above the ground with an initial speed of 20 meters per second. It strikes the ground 10 seconds later. Determine the initial height of the rock above the ground. Okay. Very, very similar argument. You're going to go with this. Now again, if there was a throw, up in the air, and then the thing's going to come down, that's a lot going on. I mean, if something gets thrown upward and then it comes down, you got to worry about the signs of how you're actually reporting stuff. But if something is, you always, and in terms of gravity being concerned in such matters, G is always negative. You can make G positive if your whole entire reference frame without exception, is everybody downward, then G is negative in the strictest sense. Distance is also negative. V is also negative. If they're all negative, you can multiply by -1 in the mathematics and make everybody positive. And that's what we did for problem number 14. For problem 15, it's the same exact argument. So what we have here, D is VIT. There it is. Here we go. Let's find out what the height was. It's a little easier. The height is D. 20 meters per second is the magnitude of velocity. It's traveling for 10 seconds. Aided by that is the fact that you've got gravity. Everybody's regarded as positive in this whole matter. Everybody's regarded as positive because everybody's going down. So you got that. I'm sorry. I don't know where I got that 20. That's from the speed, I think. All right. Grind out the mathematics, folks. For that to take place, again, no resistance due to the air. No air resistance for our purposes. All right. That's 15. 16. A rifle is aimed horizontally at the center of a large target 200 meters away. The initial speed of the bullet is 400 meters per second. What is the distance from the center of the target to the point where the bullet strikes the target? The bullet's going to fall because the person did not compensate for the fall. It's just going, the bullet's being fired straight at it 200 meters away. By how much is it going to fall? Well, let's find out how long it takes to get there with the horizontal component of velocity, and then that amount of time that it took to get there is that amount of time that it has to fall according to d equals 1/2 gt squared. So it shouldn't be too bad. See exactly what we want to say here. Kind of put the carriage in front of the horse a little bit on this one. 16, the way something falls is according, if it fall, the component, the fall down component, there is no vertical component of velocity, so it's 1/2 at squared. The d, the amount of fall, the a is equal to g, it's going to be 1/2 gt squared. G is 9.8. 1/2 of 9.8 is 4.9. This is what the answer is going to be if we can just find out what the time is. How long does it take to get there? Well, there's a horizontal component of velocity. You're going a distance x with a horizontal component of velocity for a time t. Let's find out what that time is. The time is going to be the distance traveled divided by the horizontal component of velocity. X is 200 meters away. 200 meters away is where the target is. The x component of velocity is the way the gun was fired, at 400 meters per second horizontal. Here we go. T is equal to 0.5 seconds. That is the time of travel to get to the target. It will fall for 0.5 seconds according to this equation. So what you end up having here is the d, the amount of fall, is going to be 4.9 times this. D is going to be 4.9 times 0.5 squared. That right there is a quarter. 1/4 times this is 1.225. And it'll fall quite a bit, actually. 1.225 meters is the way it fell. So that is 16. Okay, and there's a round off there, 1.23 meters. Quite a bit, though. Quite a bit. If it's fired horizontally. So again, compensation has to be figured out. To hit the bullseye, there has to be some sort of adjustment made to make that happen. Which is its own fascinating mathematics when we do stuff like that. All right. Let me see here, guys. Let's do 17, 18, 19. It is set up in a rather fascinating way, and we've done a lot of the mathematics that gets us there. And let's kind of take it from there. All right, so let's do that. Make sure everybody can hear me, guys. I don't know when this thing got shut off, so I'm just going to keep it. I think rather than attach it in a particular way, I'm going to need to kind of, let me see if I can do this. Just testing it right now. Yeah, it seems to be working fine right now. So, okay. All right, guys. If I have to do a little bit of a voiceover again on some of the stuff, maybe I'll do that. Otherwise, I'll just have people look at it, and we talk about some of this stuff in person. We'll see. I'd prefer to have people be able to hear this stuff. So let me Let me go. Let me keep going with this, guys. Let's take a look at 17. They got an interesting problem. You just read it and go for it. So again here, this is, for some reason, I've got this numbered in kind of a weird way. That should not say, use the following information. Use the following information and drawing for problems 12 through 15. That actually should be I have no idea where that came from, guys. Some of that must be a typo on that. Don't sweat it. Don't care too much about it. This is going to be 17, 18, and 19. So 17, 18, 19, and 20. I just misnumbered them 12 through 15. It might have been from another exam or something like that. That's not our issue. We can overlook that. 17, 18, 19, and 20. Let's take a look at some of the pretty fascinating aspects of that particular problem and see what we can do with it. Okay. They've got a setup here, and we need to just see some of what goes on regarding it. So let's see what we have here. They've got, so this will be for, again, it's just a typographical error in the actual problem, in the actual hard copy of this, the 12 through 15. Should not be 12 through 15. It should be problems 17, 18, 19, and 20. It should be 17 through 20, not 12 through 15. My fault. They are telling us it's a frictionless surface on which the item, any contact being made here, it's a frictionless surface, and the acceleration due to gravity is g is 9.8 meters per second. The masses under consideration are going to be the classic three bodies on a table, the three, three masses on the table, three-body problem, I guess you could say in a sense. In more complicated mathematics, it's actually three-body problem means something different. It's a little more complicated. The mathematics is very complicated. I don't know if they've ever solved some of the more challenging aspects of the three-body problem. But for our purposes, this is pretty basic stuff, but still pretty fascinating in its own right. We've got this. Forgive me, guys. All right, okay. Very good. So let's see what we have here, guys. From previous mathematics that we've done regarding this, we've got, this is M2, this is M3. Try to draw these to some kind of a scale, folks. This is M1. There is a tension T1 here, same tension here, Newton's third law. T1 there also. T2, and this is T2. Again, Newton's third law we talked about. We know there's gravity under consideration, but it's not really drawn here, but it's inferred that it's got to be present. 17, 18, 19, 20. Let's see how I want to proceed with this exactly. There's a lot that goes on. How we want to actually do this, how we want to actually look at this, guys. You can look at what's going on here, guys, and how this whole thing is going to proceed and how you want to get this and how we want to get answers here. If this thing right here is the most massive, and it's pulling down like this, M3G, this location here, and then this location here, let's actually number them. And then this location here, there's going to be all kinds of tug of war going on here, but the way we're kind of looking at it, now this is not going to be a great drawing, but this is M1G. For some reason, we're seeing this thing. This thing right here is stronger than that. This is scenario 1, or this is location 1. This is location 2, and this is location 3. And inside of this, all the physics that we need is there for each one of those. We're assuming there's an acceleration taking place this way. And since they're all attached, there's an acceleration taking place that way, and there's an acceleration taking place this way. So what's going on here? So for number 1 scenario, and we've done this before, T1 minus M1G, the difference between the two, is the acceleration of M1. T1 minus M1G. There's a tug of war going on, folks. There's a tug of war going on here. T1 wins it. By how much does T1 win it? T1 minus M1G is the difference, and that results in this mass being accelerated with acceleration A. So just look, forget all the other things going on in physics. Once you get into one of these, whether it's number 1, number 2, number 3, once you get into scenario number 1 or scenario number 2 or scenario number 3, when you separately get into scenario number 1, this is all that counts in the universe for our purposes right now. Just for the math, for the physics of this particular location, this is all that will count in the universe. T1 minus M1G, that difference is M1A, and that's this. For here, the tug of war here, this guy wins it. T2 minus T1, the difference between the two is M2, M2A. And let me put the A here, guys. All right. Let me go to 3. 3, there's a tug of war. This one wins it. It's M3G minus T2. and that results in an acceleration of m3 with acceleration a. They all have acceleration a because they're all tied together. Once we have this, we essentially have everything that we need to solve all four problems, or close to it at least, or very close to it at least. So what you have here is this. And there it is. Now, so a lot can be said. Definitely there's a lot can be said, I guess you could say. We can say the following. What is the magnitude of the acceleration? What is the magnitude of T1? What is the magnitude of T2? And then they're saying some other stuff there. It's not that bad. I think we got a lot more than you think. I'll tell you what I'm going to do. If you want to find the magnitude of the acceleration, what is the magnitude of the acceleration? Just play the mathematical game right here. You do know what M1, M2, and M3 are. You don't know what the, they gave you. I mean, you know what G is, it's 9.8. You know what M1 is. You know what M2 is. You know what M3 is. You know what G is, as we just said. We don't know what A is. We don't know what T1 is, and we don't know what T2 is. A, T1, and T2, if we find A, T1, and T2, we should be okay. If we find A, T1, and T2, we've answered three of the problems. We do have three equations, folks. We have three equations and three unknowns. So we have three equations in three unknowns. That's it. Linear algebra tells us three equations and we have three independent equations and three unknowns. We can solve for the three unknowns. We got three of the problems solved. Tell you what I'm going to do. Let me solve for A. Let me add M1A, M2A. Let me add all three of these equations together. M1A plus M2A plus M3A is M1 plus M2 plus M3 times A. M1A plus M2A plus M3A is the quantity M1 plus M2 plus M3 times A. If it's going to be M1A, M2A, M3A, factor the A out and you got this. Add these together. T1 and add them all together. Let's see what we can do. T1 and negative T1 is 0. T2 and negative T2 is 0. M3G minus M1G and let's just go back for a second. If you add those three, just what the heck? Let's just kind of be a little more rigorous about it. What I said was true. Let's just kind of verify it. This is M1A. This is M2A. This is M3A. Factor an A out. Factor a G out. Divide by this on each side. Divide by that mess of a quantity on each side. You got M3A minus M1, M2, M3 here times G. Folks, you already kind of knew a lot of this stuff, and there's other ways you can do this to actually draw this conclusion, but let's go there anyway. This will get you there. This will get you there for what we want. So what we're doing let's see what we can say here, guys. Let's do the math, I guess you could say. M3 is 800. M1 is 200. M3 is 800. M1 is 200. 800 minus 200 is 600. 200 plus 400 is 600. plus 800 is 1400. 600 divided by 1400 is 6 divided by 14 is 3 divided by 7. 3/7 of g is what the acceleration is going to be. So 3/7 of, you just plug in all the numbers, grind it out, guys. So for 17, again, we did it. I mean, we said we did all the mathematics. We added all three equations together. It brought us to here. We factored out the a on the left side. We factored out the b on the right-hand side. We divided by the quantity in front of a, that entire sum in front of a. By that, we divided on each side, and we got a is equal to this. This was 800 minus 200. That's 600. This is 200 plus 400, which is 600, plus 800 is 1400. 600 divided by 1400 is 6 divided by 14 is 2 divided by 7. 2/7 of 9.8 will get you there. And what you get is, the answer for this is 4.2 meters per second squared. Yeah, it's not going to go into free fall. The only way you can make these guys go into free fall in circumstances like this is to cut the ropes. The ropes are kind of stopping, there's a lot being dragged around here. And there's some stuff that's just not contributing to it. Either you make the table disappear and they all fall in, if you get, somehow you make the table disappear, they all fall at 9.8 meters per second. Or if you cut the ropes, then the two edges, the M1 and the M3, will fall at 9.8 meters per second. And the M2 won't move at all. So that is number 17. Number 18, there's a lot that goes on, guys. I said for this guy right here, can I make some comments? Well, yeah, I think so. We can say, let me solve for T1. Let me add a positive M1G on each side. And then T1 is M1A plus M1G. I took equation number 1. I took equation number 1, I added M1G on each side, and T1, equation number 1, add M1G on each side, I get T1 is equal to M1A plus M1G. Can this be written like this? Factor the M1 out, and you got this. I think it's a little easier to look at. So you got this. This is how you write the formula for T1, because they're going to ask us that. See what else we got. For T2, okay, this is what they gave us initially, guys. I'm sorry I'm writing all over the place here. I'm trying to hold on to this stuff so I can actually get the answers over there. For T2, how are you going to solve for T2? There's probably a number of ways you can go here, but this might be the easiest. Add a positive, solve for T2. Get T2 over to the left-hand side. Add a positive T2 on each side and subtract M3A on each side. And you get, so add a positive T2 on each side, subtract M3A on each side. You get M3G minus M3A equals T2. M3, let's just see how I wrote that, guys. Forgive me. M3, it's going to be M3G minus M3A minus M3G minus M3A. M3G minus M3A is going to be, forgive me, guys, it's probably, I'm messing this up more than I'm helping it, but all right, let me pull out an M3 on each side. Pull an M3 out of there on each side. Okay, well, now we got two other formulas. We basically solved, we already solved for A. We already know what A is. We can plug it in there and figure out what's going to be. You are essentially, let's see what we got here. They want what is the tension, so they got, let me kind of cut to the chase on this. I'm taking a little longer than I wanted to take on it, but let me see what I can say here. Okay, right, okay, still functional. Let me see. Okay, so we got the acceleration for number 17. 18 and 19, you got to get T1 and T2. So that's 18. This is 19. T1 and this is T2. Well, T1 we said what it was. We got the 4.2 meters per second, number 17. That was the acceleration. So number 17, the acceleration was 4.2 meters per second. T1 is going to be this. Well, let's do it. Didn't we say, well, let's do it. Here it is, T1. Let's just see if we just walk through it. T1 is equal to all this. G is 9.8. 9.8, 9.81. Okay, let's use 9.8. This is 9.8. A is 4.2, which is pretty convenient. 9.8 plus 4.2 is 14. 14 times M1 is 2,800. So we're getting that. Let's just confirm it. I don't want to get too adventurous with this. Absolutely. Let's see what the other one is. Well, we'll just go through it again. Give it a quick one to look at it. This is this is T2. This is T2. This is 9.8. So we're going to get T2 now. This is 9.8 minus 4.2. That is going to be 5.6. 9.8 minus 4.2 is 5.6. 5.6 times 300 is an interesting question in its own right. It should be, I'm trying to kind of look at it there when we do it. Yeah, right. 5,460, something like that. Don't quote me on these. Let's look at it. I'm saying 5.6 times that, 4,480, something like that. Let's see. We grind out the number. There it is. Yeah. So the big thing is, could have been a lot harder problem. We could have put friction in there, guys. Those of you in the non-calculus treatment, of mechanics and heat have seen problems that have friction in it. Those of you in the calculus-based treatment of mechanics and heat have also seen friction associated with a problem like this. There could be in the non-calculus-based treatment of mechanics and heat, there could be a frictional component associated with this. Also, in the calculus-based treatment of mechanics and heat, there could be a frictional component associated with this. Not incredibly much harder, but it's there. I mean, it's there. We've done it. Those of you who have had me, we've emphasized both circumstances, where the tabletop could have friction associated with it, as we have here, no friction associated with it, or there could be friction associated with it. The equations here changed a little bit. The top equation doesn't change. Equation number 1 doesn't change. Equation number 3 does not change. Equations 1 and 3 do not change when there's friction present, but here it does, because then you go subtraction mu sub k, subtraction mu sub k m2g. That's it. It's just still 3 independent equations. It's still 3 independent equations and 3 unknowns, and it works. It would, a little different dynamic. We don't have to. I don't want to beat this thing up too badly, but this would happen if you could bring a mu sub k in here, m2g, And there you go. You got 3 equations and 3 unknowns again, 3 independent equations and 3 unknowns, and there's a frictional component going that way, opposing the motion. And all the mathematics is really similar, just a little more complicated, and we've done problems like that. So something of interest. We don't need to go there. I mean, we're not being asked that right here. When we are asked that, we'll figure it out. Or if we're asked that even. Okay, so we've got that. I mean, you're asked that in other places. I mean, you can be asked that in other places, obviously. So we got this. We'll see, we'll see what happens. Okay. We've got 17, we have 17, 18, and 19. Let's talk about 20. 20 shouldn't be too bad. We have all the data that we need. We should be able to pound right through it and be okay. 20, assuming very long, let's just assume this is a very big experiment. Huge, is as big as a city block, so to speak, and very tall. And let's say there's no friction associated with anything here, and the ropes are long and the ropes are massless. How does something fall? How far does it fall? Let's talk about it. Number 20, assuming very long, light ropes and very much space to reach the ground. Assuming very long, light ropes and very much space to reach the ground, how far will M1 climb in 4 seconds? How far will he climb in 4 seconds? Well, okay, guys, I'm going to try to put the 20 right here. Forgive me. Let me just try to kind of look ahead a little bit. I want to make sure. Okay, yeah, they're going to do it again to us. That's all right. Okay, I'm glad I wrote this stuff on there. We're going to right afterwards. I kind of foreshadowed what we're going to see, so we're going to figure it out. All right, I'll tell you what I'm going to do. Good. I can leave a lot of this stuff up here at least, I guess. Let me figure out what I've said, and let's see what we can do for 20, you guys. So, let's see if we can make this make a little bit of sense, and maybe hopefully do this in an efficient manner, I guess you could say. It's a lot easier than you think it is, so let's do it. It is going to climb. You saw how the motion's taking place, guys. The direction of for our purposes, I don't want to get too far into this because that's not always what I'm about to say is not always the case, but in this instance, it's somewhat obvious that the direction of the acceleration is the direction in which the motion is going to be occurring, and they're all tied in together, so they're all accelerating the same way, they're all moving with the same velocity, and they're all moving, how would you say this? Let me see here. They're all moving clockwise. So there you go. How far would that thing climb, M1? Look, I could just easily say, how far to the right is M2 going to move in 4 seconds? How far down is M3 going to move in 4 seconds? Or how far up is M1 going to move in 4 seconds? The answer is the same for all of those because they're all tied together. The ropes aren't stretching, they're light, and the whole thing, and everybody's going to move. Everybody's going to move the same amount of distance in 4 seconds. What is that distance? H is equal to D times 1/2 AT squared. H is equal to 1/2 the acceleration that we discovered, 4.2, for 4 seconds. Grind those numbers out. In 4 seconds, $33.6 meters. the acceleration. Now, where's the VI? We're saying initially it was at rest. That's the assumption we're gonna say here. We had this thing take off. Assuming for number 20, assuming very long light ropes and very much space to reach the ground. How far will M1 climb in 4 seconds? We'll assume it starts at 0 seconds. Well, yeah, we'll assume it starts at 0 seconds. That's reasonable. We'll assume that it's not moving. It does matter if it's already moving. If it's already moving, then you got to bring in, something different. If that's the case, you got to bring in the H is going to be VIT plus 1/2 AT squared. If it's already moving, we're going to assume this thing started from a dead stop. You're using this kinematic equation to get what you're going to get, guys. And that's what we use. Use that kinematic equation. We're saying it started initially at rest, and you got this right here. 1/2 times 9.8 times 4, 1/2 times 9.8 times 4 squared gives you that answer. And that takes you 17, 18, 19, 20. Okay. Let's see if we can kill a couple birds with one stone, you guys. Very, very similar kind of argument. I guess fortuitously, I foreshadowed some of what we would see. Forgot that we did have with the friction present, and that makes a big difference. All right, guys, if that's the case, let's look at problems. Here, you guys, let's look at problems. Again, I have no idea how I'm writing. Even here, I wrote, use the following information and drawing for problems 16 through 19. No. For problems 21, 22, 23, 24. So forgive me on that one, guys. But they're saying a lot of the same stuff. They're saying that for this next one now, for 21, 22, 23, 24, M1 is 200, M2 is 400, M1 is 200, M2 is 400, M3 is 800. 200, 400, 800, same thing, everything the same. All right, so please ignore the typos. One had 12 through 15, and the other one is 12 through 15, and the other one's 16 through 19. It should have been, what do we say, 17 through 20, and the other one, 21 through 24. Problems 21, 22, 23, 24, they gave us this. They told us, now it gets, hopefully makes some sense here. You're going to assume guys, everything I drew up here is valid with the exception of one thing. Now assume friction on surface. For 17, 18, 19, and 20, there was no friction on surface. Now for 21, 22, 23, 24, there is friction on surface. Now assume friction on surface you guys, with coefficient of kinetic friction equal to 0.2. And we are on Earth with G equals 9.8 meters per second. M1 is 200, M2 is 400, M3 is 800. That's good too. They are telling us that mu sub k is 0.2. That is something that was not present before. Mu sub k was 0 before. Please watch carefully, guys. The same situation, but the value of A is likely to be different. And we'll ask why. We've got this right here. Try to figure out how I want to write this. We've got this right here, and it's a bit exaggerated, but this right here is the force of friction, and it's equal to the normal force times mu sub k. Well, the normal force is the straight down M2G. So that right here is a part of this whole thing. All right, so it gets a little, I got to change this a little bit. Not a whole lot, but enough. That's 2. There's the force of friction, folks, going this way. It's fighting everything that's going on. Well, what does that tell you? Forgive me here, I had to get a little more chalk here. What is that telling you? Well, my gut feeling, and we've already talked about this. We've been here. We've been here, folks. I mean, we've talked about this before. There's even very recently, I say, hey, hypothetical situation. Well, that hypothetical situation is now the reality for problems 21, 22, 23, and 24. We were doing problems 17, 18, 19, and 20, which looks very, very similar to this. Now, the next group of 4 problems, as we said, looks very, very similar to this. Right here, it's very similar, only now we have the force of friction that wasn't present in 17, 18, 19, and 20. Now, for 21, 22, 23, 24, the force of friction is present. Everything else is the same. The drawing's exactly the same, but now I drew the idea that there's going to be the force of friction, you guys, that wasn't there before, and that's associated with that right there. For number 3, notice there's no friction for M3 that's hanging here, and there's no friction for M1 that's hanging here. There's no frictional, because the pulleys have no frictional force for our purposes right now. We're not going there in this particular part of the practice exam. But the pulleys are massless, the ropes are massless, the pulleys are frictionless, and the surface was frictionless for problems 17, 18, 19, and 20. But now, for problems 21, 22, 23, 24, everything's the same except for there's friction right here. There's friction right here, but there's no friction here. Not in the pulleys, not in the air, no air resistance, no anything. This holds, which means equation 1 holds, and equation 3 holds. Yes. Equation 2, you got more going on here. You got T2 winning the day. Now again, the acceleration is going to go downward over here, upward over there, and sideways to the right over here. It's going to go counter, let me just look at my watch. Yeah, it's counterclockwise. Same, now it's going to be a different A. My gut tells me that the acceleration experienced by these 3 bodies in this 3-body problem, the experience of these 3 masses is, you look at it, okay, there's a lot of similarities here to previous things that we just did. What's the difference? There is a frictional component on the table. If there's a frictional component on this table, everybody's going to get slowed down, which makes sense. There wasn't friction before, so there wasn't that slowdown aspect that was going to occur. Here there is a slowdown aspect because there is friction. My gut tells me the frictional force is going to create a situation where the acceleration is less than what it was earlier. Where earlier, everything's the same as it is here, except for the fact that earlier there was no friction. But the masses are the same, table's the same, pulleys the same, ropes the same, the whole thing. But the fact that there is a frictional component, there's friction going on here where it wasn't going on earlier, this is all going to get slowed down. Acceleration's not going to be as great. First thing on our mind. Second thing, if acceleration gets slowed down, there's some pretty interesting things that happen. Come over here. If acceleration is smaller, when you add these two, the sum is smaller than it was before, so T1 is going to be smaller. Which makes sense. Well, maybe it does. Maybe it does, maybe it doesn't. That's another idea in its own right. But if A is smaller, than what it was earlier because of friction, smaller a, if you just add the, notice all this mathematics, T1 minus M1G equals M1A, and here M3G minus T2 equals M3A, M3G minus T2 equals so M3G minus T2, M3G minus T2, that difference is M3 times A. For the other one, T1 minus M1G is M1A, is M1A equals T1 minus M1G. So M1A equals T1 minus M1G, M1A equals T1 minus M1G, and M3 equals M3G minus T2. Those don't change. The A is going to be different because this is going to be different. That's the interesting thing. What happens here is this guy's pulling, he wins, but he's not only being fought by T1, he's being fought by this, which is the force of friction, which is mu sub k M2G. So what happens is, regarding this, so let's see what happens. I mean, when you do this, it's going to be similar to stuff we've done before, but let's be careful. It's T2 winning the fight. T1 is fighting T2, and so is F, which is mu sub k M2G. So you subtract mu sub k M2G. That's all that changes from the previous 3 equations and 3 unknowns. We still have 3 equations and 3 unknowns. We know what G is, we know what M2 is, we know what mu sub k is, they told us. We know M3, we know M1, we don't know A, we don't know T1, we don't know T2. There's 3 unknowns, but there's 3 independent equations and 3 unknowns, just like we had earlier. This is now the reality. Not too far off, not too far, but it's different. It's certainly different. I mean, let's not think otherwise. It's not, but this is now the reality that we're looking at. So if this is the case, let's see what we can say. See what we can say on this. But the other ones don't change. And what's interesting about that, because the other ones don't change, these don't change. But the numbers are going to be different. In this situation, acceleration is smaller. Smaller acceleration than what you had earlier when there was no friction. Smaller acceleration now with friction than what you had earlier. Smaller acceleration now than what you had earlier. Now you have friction. The acceleration is smaller in the whole system. Smaller acceleration than what you had earlier means this T1 is a smaller answer. Here, smaller acceleration means when you subtract, you get a bigger answer here. So T1 becomes smaller, but T2 becomes bigger. That's strange. That's very strange. So you're saying for this to take place, T1 is smaller, which makes sense. If T1 is smaller, there's not as big of a victory. If T1 were smaller than what it was earlier, if T1 is smaller than what it was earlier, smaller minus this is a smaller value for that, which means a smaller acceleration. We already knew it was going to be a small. The only way you can get a smaller answer here, M1 ain't changing, the mass ain't changing. A has to be a smaller value. And for A to be a smaller value, T1's got to be smaller. This guy can't pull as forcefully to make this thing go with a very strong jolt, which makes sense. Acceleration is smaller. So T1 would have to be smaller. Here, T2 would have to be bigger because this guy can't fall as fast. If he's bigger, there's more of a fight that takes place, and then this is a smaller value. The only way you can get a smaller resultant force is if A is smaller. And that can happen only if T2, because these guys are constant. M3 and G are constant. M3 is also constant. If this guy's smaller, that guy's got to be bigger for this to be a smaller answer, because the bigger guy fights this guy. This is a bigger answer. T2 is a bigger answer because it prevents it from falling as fast. So T2 is bigger than when it was earlier when there was no friction. T1 is smaller than what it was earlier because it can't pull as hard. So the upward pull is not as strong, so T1 is smaller. The upward pull to get this thing to go upward is smaller than what it was when there was no friction, which makes sense because there's friction, there's not as much acceleration. So this is just not able to pull as hard. Not going to pull as hard to make it go to the acceleration that was going on earlier. So T1 overpowers this, but not by as much as it did earlier because there's not as much acceleration. T1 is smaller when there is friction. T2 is bigger when there is friction because this will prevent the fall down from being as fast because there's friction. Interesting. But notice these guys stay. These guys stay. You don't need to deliver a speech like this when you're doing a final exam. Just know how to do it. But this is the stuff you're talking about. Now you could say to me, okay, well, you're saying a number of things here, so let's see what we can say about it. Well, there's 21, 22, 23, 24. They want the acceleration. They want T1. They want T2. And then there's some other thing that we're going to put on there. So we'll get to it. Before we go there, let's do the same mathematics we did earlier. 3 independent equations in 3 unknowns. The 3 unknowns are A, T1, and T2. 3 unknowns, and here are 3 unknowns in 3 independent equations. 3 independent equations and 3 unknowns. Let's add all these. Let's add all these. Let's do the same math we did earlier. Let me add the left-hand sides together. Let's add all the right-hand sides together. Here we go. Let's be careful. T1 and negative T1 is 0. T2 and negative T2 is 0. Yeah, but that minus stays. M3G minus M1G minus mu sub k M2. Let's see here. Let's see. Yeah, so I got M3G minus M1G minus mu sub k M2G. That's pretty big. That's a pretty big conclusion to draw here. You draw to here. All right, let me see what we can do. Pull the A out. M1, M2, M3. Here's A. Sorry, guys, running out of room here. Okay. That's the, I factored an A out of the left-hand side. I will factor a G out of the right-hand side. Okay. Don't want to highlight this stuff too much yet. If I highlight everything, it's hard to see anything. There's a G right here, and there's that right here. Divide by the sum divide by the sum of M1, M2, and M3. Acceleration is, and again, guys, I'm sorry, there's just no room. Maybe I write too big, but I want to make sure. So it's M3G minus M1 minus mu sub k M2G. No, M2 rather, yeah. U sub k M2. The whole thing's got a G here. Okay, sounds good. All right. Still not great, but okay, a little bit better, maybe. Divide by this quantity that's in front of A on each side. M3 minus M2 minus mu sub k M2. That's what wasn't there before. There it is. That's what your acceleration is going to be. Notice the mathematics present betrays the reality of the situation. In plain English, A is going to be a smaller number. Why? Because in the past, we had this. We had M3 minus M2. We had M3 minus M2 over the sum M1 plus M2 plus M3. All of that ratio times G. We had the quantity M3 minus M2 over the quantity M1 plus M2 plus M3. That entire ratio, that entire division times G. Here you got the fact that there is friction, which is going to make A smaller. When you get that A, you can use the exact same equations. Because these guys on the outside, right here and right here, right here and right here, they don't change. There's no friction. The mathematics is what it is. The A is not the same. This changes the A, which means these are going to be different numbers. But the actual setup right here and the setup right here is identical to what it was earlier in problems 17, 18, 19, and 20. Well, okay. See what we can say, guys. They are asking, let's go. I'll do 24 kind of separately. They're asking for 21. 21, what is the magnitude? Forgive me. Yeah, right. 21, what is the magnitude of the acceleration? 22, what is the magnitude of T1? 23, what is the magnitude of T2? That all sounds very familiar. Yes, be careful with the mathematics. Let's go. Here we go. Remember, it was 4.2. It's going to be smaller than 4.2. We're anticipating the entire argument that we gave earlier. It's going to be smaller than 4.2. So let's see what we got. 4.2 meters per second was when there was no friction. When this wasn't here, and you had this situation, times G. M3 minus M2, get an answer, divide it by the sum of the following three quantities, M1, M2, M3. Get that answer, multiply by G. Yeah, it's going to be 4.2. Not now. Now it's going to be, there's a lot of ways to write it. Right, absolutely. So what we have here is, let's just do it. This, and I wrote it in different order here. Doesn't matter who you subtract first. You can go you can subtract mu sub k m2, then minus m2, or let me see here. Now, forgive me, guys. This has got to be something a little different. It's got to be an m1 right here. I'm sorry. This has got to be an m1. My fault. m1. Okay. Everything, and that was right here. I don't know how I managed not to write that. Okay. Let's do it. Looking at this right here, you've got 800. You've got 800 minus 200 is the 600. Remember, we had 600 over 1400. Right? 600 over 1400, which gave us, the 3/7 that we were talking about, right? But not now. This is 800. 800 minus 200 is 600. 600 minus 0.2 times 400 is 80. 600, so 800 minus 200 is 600. That's what we had earlier. Now you subtract more. 0.2 times 400. 0.2 times 400 is 80. So 800 minus 200 is 600. 600 minus 80 is 520. This is 1400. 520 over 1400 times g, right? 520 over 1400 times 9.8, the ratio 520, the ratio of 520 over 1400, 520 divided by 1400 times 9.8 is 3.64. And that is smaller. That is smaller than the 4.2. And then we thought it would be smaller. Okay. Well, then you got to put that into all the places. A is 3.4, and there's where we're going to get the things that we talked about. You're going to put, forgive me, 3.64 rather, right? 3.64. You're going to put 3.64 plus 9.8, get an answer, and then multiply it by 200. And that's going to be what T1 is. And we said that was going to be smaller than the other T1. The other T1 was 2,800. This is a little more, this is a little short of 2,700. The other one was 2,800. So we got to here. The other one should be bigger than the other one was. And I don't have it right in front of me, but it was something like, if I remember that thing correctly, guys, how they actually did that. We said it was, right. We can look it up. It doesn't really matter. But here we got 9.8 minus 3.64. That's going to be a bigger number than 9.8 minus 4.2. 4.2 is what it was earlier. It was 5.6 times this. Yeah, and that's what we got the 4480. This is not going to be 4480. It's going to be bigger than 4480 because this minus this is going to be bigger than 14. Forgive me, it's going to be bigger than the 5.6 that we got. 9.8 minus 3.64 is going to be 6.16. That's bigger than 5.6. That's going to, the 9.8 minus 3.64 is 6.16. 6.16 as a difference here is bigger than 5.6. So when you multiply it by 800, it's going to be bigger than the 4,400 that we were talking about last time, 44 something. And it comes out to 4928. It's all the stuff we've talked about. Forgive all the talk, guys. You don't have to deliver a speech like this when you're taking an exam. And if you get this stuff pretty well, you don't need to explain it out loud. I mean, if somebody's trying to... Yeah, absolutely. This is smaller, as we said it would be, than the other T1, which was 2,800. This is bigger than what we had earlier, than the 4480 that we had earlier. So let's see here. Right, the 4480, so it's bigger. We said that. We already talked about that. For 24, they are saying, assuming very long, light ropes and very much space to reach the ground. Sound familiar? Assuming very long, light ropes and very much space to reach the ground, how long will it take M3 to fall 100 meters? It's the same kind of argument, you guys. Here's a little different. We're going to say from a dead stop. It's going to fall a distance d. It's falling 1/2 gt squared. Guys, remember, if you're doing something like that, we're assuming it's falling from like a dead stop for number 24. For number 24, you're saying, okay, d, vi, vy or whatever, t plus 1/2 gt squared. Well, we're going to assume they started it from a dead stop. If that's the case, d equals 1/2 gt squared. Well, if that's the case, if you multiply by 2 on each side and divide by g, let's get t squared by itself. Let's multiply by 2 on each side and divide by g. Then square root that. T is going to be the square root of (2d over g). Well, they're saying fall 100 meters, guys. The d is 100 meters. What's 2 times 100? 200. 200 divided by 9.8 is a little more than 20. The square root should be a little more than 4 seconds. Time out. I'm wrong. Okay, ignore that, please. This would be true if it was a free fall, a total free fall, but it's not. Please forgive that. Start that over. 24. One more time. Distance d traveled is VI or VY, VIT plus 1/2 AT squared. We ain't using G because there's ropes. We're not using G because there's ropes tied onto this system. It starts initially at 0, so D is 1/2. What I said to you would be true if it was a free fall and no ropes present. But we got to use the acceleration. And the acceleration we got here, guys, the acceleration that we got here is 3.64. We got to use that. Let's play the game one more time, guys. Let's make this happen. Let's solve for t squared. D equals 1/2 AT squared. D equals, because we said it started at 0, initial velocity. What I said earlier, like I said, if there were no ropes attached and you just cut the string, it falls like I was just about to tell you. That's not happening here. There is ropes attached and the acceleration is 3.64. It's not 9.8. Not 9.8. That was my fault. Let's solve for t squared. Multiply by 2 on each side and divide by a. T squared, multiply by 2 on each side and divide by a. T is equal to the square root of 2d over a. All right, this is it. 2 times 100 is 200. This is 3.64. What's 200 divided by 3.64? Get an answer. It's somewhere, 3.64 is 3 2/3 roughly. That's 11 over, it's 11 over 3, whatever. Goes in there, somewhere, well, let me not go there. Let's not go there. Let's just do the numbers. The way I got it solved is in square root it. T is going to be equal to 7.4 seconds. And there you are, guys. That's 24. Let's do 25, and we're done with this practice test. 25. A race car moving with a constant speed of 50 meters per second completes one lap around a circular track in 80 seconds. What is the magnitude of the centripetal acceleration of the car? It's a neat question. A race car moving with a constant speed of 50 meters per second completes one lap around a circular track in 80 seconds. What is the magnitude of the centripetal acceleration of the car? Okay, this is a nice problem as well. All right. Like I said, some aspects of some of the exams you guys, and maybe a course Well, there's a lot can be said here, guys. I mean, so this is a little more this problem is a little more complicated by virtue of the fact that there's friction. Okay, there's things you're going to see. It may be a higher level class, calculus-based class, regardless of whether you're using calculus or not. You may not even be using calculus on very many of the problems, but the problems might be a little more difficult than they would be in a class that has non-calculus treatment of mechanics and heat. So that may be the case. So the more you can practice, and there's no calculus involved, and you're not familiar with calculus, the more you can practice with the non-calculus problems, when they are more challenging and may be found in a class that's a higher level class and has, let's say, has non-calculus treatment of things, but is a calculus level class, but it's more difficult than what you might be used to seeing, it is good to look at that material. And that's the reason why these two sets of reviews for final exams, I think, are very useful for people. They're very useful for people to look at both sets. Let's say, for the course in which the courses I teach, at school I teach, the Physics 120 and the Physics 209, look at as much of both as you can. The more practice that you get, the better off that you are, I think. Okay, this is an interesting problem, the way they put it together. Let's try to make it easy. If you want to find the magnitude of the centripetal acceleration, go v squared over r. They don't give you r, but they give you the circumference. You can use 2 pi r as the circumference. If they don't give you the circumference, you can find the circumference. If the circumference is the total distance to go around one lap, if it covers, see, the distance covered is v times t. The distance is the circumference. It's going 50 meters per second for 80 seconds. That's to do one lap. To do one lap is the circumference. The circumference is 4,000 meters. They're trying to get, they're trying to get slick. Well, if that's the case, look at this. If c is equal to 2 pi r, and this is 4,000, and this is 2 pi, and this is r, whatever it may be careful how you do this on your calculator. Make sure you get the product of 2 pi first, or go 2 first, then go pi. Be very careful. You can really make a mistake here easily. Get all that done. Once you got that done, everything else becomes manageable. So what you have here is v squared is 50. R is going to be whatever that is. That's about 6 going into 4,000. And we can kind of figure it out. Let's see what we got here. We got 636.2 meters. That's a big track. So this right here, this R, is 636.62 meters. .62 meters. We got all the units okay, so we're fine. This is 2,500 divided by this, it's about 4. You grind it out, you got 3.93 . And there you go, guys. That is exam number 1 of 3 that cover this stuff. All right, thanks for your time. I'll try to get through these as best I can. Thank you. If there was a problem, like I said, I accidentally, I think, shut off my microphone, so it may show up. It may show up. So I mean, it may show up somewhere. I tried to kind of compensate for that. We'll see. If I got to do something else, we'll do something else. If not, hopefully we didn't miss too much. And within the context of the PDFs and what I'm writing on the board, hopefully it's clear for us. So we'll see. All right. Thank you so much, guys. This is exam 1 of 3, and we'll get to it. Take care.